Yeah, Zach, physics time. The best.
That's dope.
Yeah, week 5 already. Wow. Getting close. Only 2 more weeks left. What's up, Mistral? Sophie. Will the test this Friday be shorter than the last one since the last one took 3 or 4 hours? It should be about the same length. I think I'll still give you guys the same amount of time. The final, which is not this Friday but next Friday, that's gonna have like a closer window. So I think I might give like a 6-hour window for it instead of the standard like 12 you get with the midterms. But the length shouldn't be much longer. I'm trying to keep everything about the same. Yes, you're very welcome. What's up, Mistral? And Sibley. Nice. I woke up at 4:30 Chicago time this morning, so that was 2:30 LA time to get on a 6 a.m. flight, and I flew 4 hours here. I slept on the plane a lot, but I landed in LA, I think at like 9:30. And then I had to go like get my car, and so I might be a little tired. But it's okay. So if you notice I'm a little low energy, it's because I've been up for a bit. But I did get all of y'all's regrade requests done, so hopefully should see some more points on your exam. We have another exam coming up on Friday, which I need to write. That I will probably do tomorrow, because I want to see how much we get through like today and tomorrow before I decide what amount of Ohm's law stuff I want to put on the exam. Probably not too much, honestly, because I think the big stuff like Kirchhoff's laws, the loop laws, that we're all going to do, I want to say at the end of this week, but also probably a lot of like next week. So I think for people wondering like what's on the exam coming up, the cutoff is probably tomorrow for stuff, but it won't be weighted as heavily towards anything we do this week, because you've only just learned it for like 2 days. Mainly focus on what we did during the week when we had electric potential and like electric fields. Yeah, that stuff is and capacitors. That stuff is definitely gonna be heavily on the test, but some of the circuit stuff we do today and tomorrow, I'm not going to get too crazy with it. On the final exam, there will definitely be some bigger like circuit questions, some like node analysis type stuff you do. And don't worry, we'll go over it I think during week 6. I'll like intro it at the end of this week, but I know a lot of you guys are studying for the exam anyway, so I don't want to like get too crazy on bringing in a bunch of new concepts that aren't going to be tested this week. But week 6 will definitely have a lot of the Kirchhoffs and the loop laws, because that's the cool stuff, and it's very useful, especially if you end up going into any sort of like electrical engineering degree. Heavily capacitance, yeah, there'll definitely be some capacitors on there. Yeah, I'd say we spent a decent amount of time on capacitors last week, and you had a whole homework of it too. Yeah, that being said, there's a new chapter out that got released, I think, last night, which is what we're going over today and tomorrow. And that's EMF, current, resistance, and EMF. Okay, that's what it is, yeah. That'll be due next Monday, and then your last homework of the quarter will be announced on Wednesday, and that'll be circuits. And so there's no new homework after Wednesday. And then that homework's due the Wednesday before the final. And so hopefully I want to get all of your grades transferred over. I'm going to say like Wednesday afternoon next week, because that's when everything grades. I want to do it kind of like in one fell swoop. Otherwise it becomes kind of a mess trying to like sync between Kudu and Brew and Learn. But yeah. Okay. Any other quick questions before we go into current, resistance, and EMF today? Yeah, Zach, fast grading. Dude, this whole class is like super fast. I wish I had more time to like do things, but 6 weeks is 6 weeks, I guess. Can you extend the last clicker? Well, wasn't the last clicker already extended? What? That was the double lecture we did on Thursday. I think I extended it all the way until like Sunday night. But yeah, send me an email. I mean, I said I wasn't doing extensions anymore because this is week 5. We should understand how the class works by now, right? Maybe. I don't know. Okay. Let me delete this and we'll kick things off. Okay. Okay. Welcome to week 5, lecture 1. Cool. So yeah, in today's lecture, we're gonna start introducing, I guess, current, resistance. We're gonna heavily go over resistance. You kind of have seen some of this already with what we did last week with capacitors. You saw how like we set up circuits with batteries and things. We didn't really talk about how current was flowing, and we did talk about voltage at least, but this is kind of the intro lecture into how circuits work and why a battery, you know, turns on a light bulb and so forth. So first thing we're going to introduce to is electric current. Cool. So in last week's discussions over capacitance, we definitely talked about charge, right? We talked about like Q that was on a capacitor, right? And how batteries could like kind of like be like a source of this charge. They could charge up capacitors. Well, it turns out the rate at which that charge moves from, let's say, a battery to a capacitor, or moves across a resistor, or powers a light bulb, that is called electric current. And what we define that as is, so current, which is going to be measured in amps, we'll say like 1 amp, that's equal to 1 coulomb per second. Okay, so amperage, which is current, is described as the rate at which you're sending coulombs of charge into certain components or across wires, and the rate at which that happens, 1 coulomb per second, that's equal to 1 amp. Remember that like 1 electron, right, is equal to 1 times 10 to the minus 16 coulombs, right? This is really, really, really small. That's the charge on a single electron. So you could think you need like 1 divided by that. So like a coulomb is 1 divided by 10 to the minus 16. So it's like 10 to the, or it's 10 to the positive 16. Sorry, 10 to the negative 19. Thank you. Get my 6s and 9s mixed up. If 6 was 9. So there's a lot of electrons being moved in a coulomb. And if you're moving that in a second, like an amp that's a decent amount of current that's flowing through a wire. You may have noticed, if you ever have like battery chargers, or have you ever noticed on like a power pack on the back, it'll say things. A lot of times, or probably what you've seen is watts. You've seen like 40-watt chargers, 100. We'll talk about where watts comes from, but the main driver for like getting electricity, getting energy into something, is the amount of amps that are getting thrown into it, and that's again the amount of charge, coulombs, in the amount of time you're sending it there. So yeah, so that's current. We got to talk about like the flow of current. Oh, I guess where amps even comes from. It comes from French physicist André Marie Ampère. Cool. The French did a lot of cool things in physics. You got Marie Curie. You got all the other people. Let me think. Okay, there we go. Cool. Yeah. So yeah, current is number of charge. Calculating the average current. So we could do like a little example of this. Kind of real basic. But they say what is the average current involved when a truck battery sets in motion 720 coulombs of charge in 4 seconds while starting an engine. Okay, and then it says how long does it take 1 coulomb of charge to flow from the battery? So remember, right? Current is equal to, oh, I should have defined this right. So this is delta Q over delta T, amount of charge per unit time. That's going to be 720 coulombs in 4 seconds. And so that's going to get you, what is that, 180? Yeah, 180. Wait. 4 times 8, 40. Yeah. 180 amps. This is huge, by the way. Most sockets in your house are rated for 20 amps. I think even in your bathroom, they may go up to 30, but there's usually a breaker on them. And we're going to get, there's a clicker question that kind of describes like why amps are so dangerous. But yeah, 180 amps is a huge amount of power. You need a pretty thick wire to allow 180 amps to run without causing it to melt or like catch things on fire. So yeah, that is the average current. That's a lot of current. That's why, yeah, jump starting batteries is usually done with like some thicker wires, and usually there's like lots of sparks and can be kind of dangerous. And then how long does it take 1 coulomb of charge to flow from the battery? Okay, well then you just like reset the question here. So you say like, okay, well if current is 180 amps and that's equal to delta Q over delta T, right? Replace delta Q with 1 coulomb, okay? And then you can just solve for delta T. So you get, oh, delta T is equal to 1 over 180, which is the same thing as 0.00556 seconds. Okay, cool. So, oh, this is like 5.6 milliseconds. Okay. So yeah, so like a single coulomb coming out of this battery does it in like 5.6 milliseconds. Okay. So yeah, that's how charge is quantified, how we measure it. And right, the reason why it takes this much current to start a truck battery is usually what you need like, it's called a starter, but it's a separate engine or motor in your car. And what it does is it manually forces your cylinders to rotate. And in doing that, it allows the gas to then start taking over and like making combustion, and then that's what really starts the engine going. But you may have heard it. You hear like your car go like zzz, 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 zzz. That's because there's another motor taking electrical energy and trying to spin your big motor. And depending on how big the motor is, how many pistons it has, what the friction is between those pistons, it can take sometimes, yeah, I guess like 180 amps to start a like a truck engine. And yeah, that's why like bigger engines they're just more difficult to start, is because you have to beat the inertia of a bigger and bigger system of pistons and crankshafts and things. But yeah, cool. Okay, another thing that we are going to do this next week. I saw this, and this kind of relates to capacitors already, what we've been doing. What's up, Aleph? So we can talk about like instantaneous current. So right here, this was like average current is what this was. This was like average. Which is, yeah, just delta Q over delta T. You can also talk about like instantaneous current. Which is not looking at like, oh, what's the total amount of charge I moved in how much time. It's actually looking at like a function of Q and then taking a derivative. So one example they show here, and we're going to go over this later in the week or early next week. This is, for instance, the charge on a capacitor. You don't need to know this, but this is just, they show this cute little graph, and they're like, oh, I wonder where it comes from. I'm like, okay, it's charging a capacitor. So what happens is, as you have a battery, hooked up to a capacitor like this. Like, let's see, this is some capacitor. This is like some V naught. What ends up happening is that charge flows really quickly at the beginning to try to fill these plates. And then as the plates fill up, charge starts flowing less and less quickly to charge up the plates. Because it's kind of like filling up a glass of water, right? You probably like dump everything at the beginning. You're like, oh, I can do this. But then as the water glass starts filling up, you start kind of like slowing down how much you're pouring in. Because you're like, we're kind of getting towards the end. So, yeah. They could sometimes, this is a classic equation they use, where they would say like, oh, well, the charge at some time t is equal to, Qm is like your maximum charge, which in capacitors, right, that equals, ends up equaling like V times C. And then it's 1 minus e to the negative t over tau. And then this is some sort of, we call this like a rate constant. And what you should see here, right, is that as t approaches infinity, this is why limits are important. Remember when we learned limits in calculus? It's important to see here that like as t here goes to infinity, you end up getting 1 minus e to the negative infinity over, I don't really care what this is. And 1 minus e to the negative infinity is the same thing as 1 minus 1 over e to the infinity. And then you should know this. This is the same thing as 1 minus 1 over infinity, which is just 0. So what ends up happening is that the charge on whatever object you have here is eventually becoming Qm, because the difference between Qm and what you have, which is 1 minus this little bit here, eventually just goes to 0 as time goes up. As time goes up, you eventually like don't have any like less charge on it than you should. So yeah, given this is a graph of Q, you can then look at what the current would be. So this would be instantaneous current. And that's the same thing as dq dt, okay? So if you have your equation for Q here, all you need to do is take the derivative of this with respect to t, right? And what you should notice is that, okay, well, there's only one term here that depends on t, so this goes away, right? We just have this term that depends on t. And the derivative of like e to the x is just e to the x, whatever, dx, like a little chain rule in there. So in this case, you end up getting, okay, well, I is then equal to, it's going to be q, and then it's e to the, let me think, I think there's over tau. It's gonna be, you got a chain rule from here. And I think it's just going to be e to the negative t over tau. Yeah. Let's see, is that right? Yeah, q over m, e to the negative t over tau. Cool. Yeah. And this kind of shows you, right? So the instantaneous current is going down, right? As this gets bigger, e to the negative infinity goes to 0, and the whole thing just goes to 0. And you can see that with the slopes, right? So if this is a graph of current, a graph of charge, sorry, then the derivative of that thing, right, which is the slope of this function, right? You see how the slope eventually goes to 0? And this, in the frame of charging a capacitor, makes sense, because eventually there's already enough charge on your capacitor that you don't need to keep sending charge there. And so the current, the rate at which you're sending charge, goes to 0. Yeah. And so they'll end up like making this cute little graph. Pull in. Yeah. And then it kind of works. Again, I'm giving a little bit of a sneak peek on this stuff. Because it's all very highly related. But this is, for instance, what we talk about when we talk about like charging a capacitor. You'll see that, for instance, this is the Q graph, right? Graph of the charge on the capacitor, which kind of looks like that, upgoing arrow, which was, or, same curve as this. And then if you look at the current, it's a graph that goes down like this, right? Because as you fill up more charge on the capacitor, you don't need to like keep sending as much current to it. And then they end up doing some Ohm's law stuff here. So yeah, don't worry about this yet. I just want to like give a little bit of context of why we care about measuring instantaneous current, or like the amount of like charge that's being deposited on something. Okay, cool. All right, then we got to talk about the conventional directions of current. Yeah, this is always interesting. Yeah. So whenever we write, let me get black pen. Right, there we go. So whenever we draw like a circuit, so in this case, right, we have a battery, and we call like one end the positive and one end the minus, right? We usually draw current as moving from the positive side to the negative side. So here, this is positive, and then this is minus, right? And again, someone had the good intuition here, right? The longer line is the positive because you got to use more ink to draw a positive than to just draw a dash for a minus. But what's interesting is that even though current, for instance, is running here from positive to negative, we don't have like positive charges actually moving. So this is kind of the picture. It's kind of funny. This dates all the way back down to like Benjamin Franklin, when they were coming up with conventions for like how to write things. Because we think of electric field. Electric field definitely pushes from positive to minus. Okay, and we like to think of like, oh, okay, well, if there's, if charges are moving from positive to minus, and we tend to talk about positive things, then the current is also moving that way, positive to minus. But the reality is that positive things do not carry charge. Positive things in the atomic level, right, are the nuclei. That's the protons and the neutrons. Those are big, heavy things. Those things don't really want to move. What really carries electricity, what carries charge, what carries current, are the electrons, because the electrons are orders of magnitude smaller. They're usually more free, especially in the case of like conductors and whatnot. They're not really locked in place. So for this course, whenever we draw circuits and stuff, we are going to use the convention of current moves from positive to negative. So we're going to say like positive current is from positive to negative, like potential or voltage. However, just keep in mind that the electrons are technically moving the other way. So in order to like move positive charge from here over to here, really what we're doing is we're moving negative charges backwards. It's kind of the same thing in when we were talking about charging capacitors. Making a capacitor have a very positive charge on it really means you're just removing the electrons. So you're just leaving whatever's there to be like positive, because there's a debt of negative stuff, right? We don't have enough negative stuff, so overall it's positive. Yeah. So the voltage sets kind of like the gap. Again, going back to what we had this, right? Q equals VC, right? So if you have like more capacitance, it means that you're allowed to have I don't know, a bigger voltage. Well, this is actually, sorry. This is what I want to say. Sorry. Q over V is equal to C. Okay, yeah. So having a high capacitance can mean two things. It can mean either that you get to dump a lot of charge on the plates and they won't arc, or that you're allowed to maintain a very low potential difference between the two plates. And we talked about how this can be like changed with dielectrics by creating like these induced electric fields that kind of reverse the potential a bit. But yeah, there is also, there's this let me go find this one second. This is kind of a cute little diagram. Current ohms voltage graph, or it's a diagram. Cartoon. Yeah. So this is kind of how we think about electricity. Voltage is kind of like, I say in a stream, voltage is like how wide the river is. And then amps, which is current, is how fast the river is flowing water. But voltage kind of like does provide like the push. And then ohms, which is resistance, is what tries to clamp down the stream and wants to resist current flowing. Yeah. Oh, this is it's kind of a fun little graphic. There are a bunch of other like parody ones in this. I think if you look up like Anime Girl one, there's another one that's really funny, but I'm not going to show it on the stream. But yeah. So voltage is kind of like the push. Current is like what is flowing, and then we're going to get into resistance. Resistance is opposing that flow. Okay. Cool. So, yes, this being said, for directions of current, I think we have a clicker question on this one already. Let me see. Let me refresh. Nice. Okay, good. Here's our first question. Okay, so we say, which of the following diagrams properly shows both the direction and motion of electrons in the wire and the direction of conventional current, I? Which is, that's what we're going to call current in this class. It's conventional current, technically. Okay, so let's remember, right, that when we're drawing circuits, current, positive current, needs to flow from the positive to minus, we'll say, like, voltages. So in this case, this one's going from minus to plus. So that one's not right. Oh, wait, what are my answer choices? There we go. Yeah. So it can't be this one. It can't be this one either. Right? This has current going the wrong way. I like this. I like current going clockwise, right? Going from positive to negative. That's correct. But now we got to think about the electrons. So remember that if current is going this way, the motion of the electrons is actually opposite to it. So that means it's choice C. You can also think about, in terms of just, if you just want to talk about, like, you know, Coulomb force, right? The negative end of the battery is going to oppose negative things. So it's going to push the negative stuff that way. And it's going to attract positive things, which, again, positive charges don't really move. They're too big and clunky. But moving negative charge this way is creating, like, an absence of negative charge, which means you're, like, pulling positive charge towards it. Yeah, Poison says amp is the hurt. Yeah, amp is the big hurt. Yeah, we're going to talk about that. Amps are what kill you. People think it's like kilovolts and like all these high voltage doesn't kill you. That's why you can do the thing with like the Van de Graaff generator. You put your hand on it, or like, I don't know, with the balloon, make your hair stand up. That's all very high voltage situations. It's the current that's dangerous. And yeah, we'll go. I think it's one of our clicker questions. So let's see. Going through this, I think it's answer choice C. That one looks correct to me. And that is correct. Nice. Good. Okay. And then also, yeah, we can think about that here with question 2. Also talking about, this is current going across a resistor. So we might get to resistors today. We definitely will later this week, but for now, that's a symbol for a resistor. But question's asking, with conventional current flowing as shown, is point B or point C at a higher potential? So remember from before, we talked about that current runs from higher to negative potentials, voltages, you know, yeah. So in this case, if current is running this way, this must be the positive end, and then this must be the negative end, right? If we had like some, well, let's say we had a battery or something, right? Yeah. So this would represent the negative end of the resistor, which means it's at a lower potential. And then this is the positive end, because it's at a higher potential. And then again, current is flowing from high potential to low potential, or high voltage to low voltage. So I think point C is at a higher potential. So that should be choice B. Correct. Good. Okay, cool. We're making progress. Good. Awesome. All right, then we're going to go to, resistance and resistivity. Okay, any questions before I move on with this? Any questions about like current, charges, why we're choosing things to be certain directions? Let's talk about, we're going to talk about like drift velocity and conduction. Yeah. So remember earlier we talked about how like conductors, you know, allow, well, we said like they like conduct electricity, right? In this case, we're going to say they allow current to flow. And the reason for this is because you have electrons that are more or less free. Say like free to move. They're not locked in place like non-conductors. However, these electrons they don't run in a straight line, okay? Because what happens is you have a lot of stuff in the way. So yeah, here they have this little cute little picture. So let's take the case of, let's pretend again that we have a positive charge here, a negative charge here. Oh, sorry, negative voltage potential. Sorry. So that means you're going to have an electric field. Let's draw an electric field in blue. That points that direction. And that's also going to mean that like the current is flowing in this direction. Okay. And remember that current, even though conventionally we're saying current's running here from positive to negative, in reality what's happening is that the electrons are being pulled in the opposite direction. Now, the electron here doesn't get pulled just straight to the right. It doesn't just zip right over there. Yeah. It like bumps into a bunch of stuff. So it hits the walls of, you know, whatever material it's in. It bumps into other atoms. It bumps into other electrons. So what ends up happening is we say that these electrons have a drift velocity. So this is called electron drift velocity. And it's kind of like the average speed at which the electrons are moving in your conductor. Now, you might be tempted to say, well, electricity is really quick, right? The internet is super fast, like data, right? All that stuff has to be moving really, really fast. Shouldn't the electron drift velocity be like close to the speed of light? It turns out it's not. The electron drift velocity can actually be really slow. It can be like centimeters per second. Like it can move really, really slow. What carries the information, however, is very fast, and that's the Coulomb force. So you can think about that like as this electron bounces around, other electrons are bouncing around next to it, and the interaction of those forces, that's what like carries electricity or carries current, and that travels at almost close to the speed of light. So even though the electrons physically, like this physical electron at the left is not going to get over here to the right in a short amount of time, it's actually going to like take it a little bit. The amount of interactions it has with other electrons carries the information of electricity moving much quicker than this individual physical electron is moving. So yeah, it has to do with like, yeah, drift velocity is actually not very large. Drift velocity is usually quite slow because getting a totally free electron to just bounce around is quite rare. More often than not, it's kind of like the electrons are like bouncing into each other. There's a name for this like type of machine. Do you guys know what I'm talking about? Like with the balls and stuff. Balls swinging. I gotta be careful what I type into Google. Yes, exactly, Sophia. Yes, the bumping of electrons and the repulsive forces, that's what actually makes electricity move very quickly. Yes, drift velocity is a very low number. We don't really use it. It just always gets taught. And it has some significance in some other quantities we're going to use, which is like resistivity, and what's the other? It's just let me see. Yeah, and like current density. In the practical sense, all you really need to know is how to calculate resistance. Resistance is really what we care about, but they like going into this little side tangent of like what is resistivity and how does resistivity give rise to resistance, and how is that resistivity related to or defined by how fast electrons drift in a material. So you can think about like if something's a better conductor, has more free electrons, then it probably has a higher drift velocity because the electrons as a whole probably move quicker. But the actual, speed of electricity, I'm pretty sure is close to the speed of light for any material. The amount of electricity, though, the amount of current you can push through, now that starts depending, again, back on the resistance, which depends on the resistivity, which depends on the drift velocity. So I see why it gets taught, but for practical sense in doing questions, you don't really use drift velocity. It's I'll show you how they're related. But okay. I wanted the balls swinging in each other thing. Newton's cradle. Dude, I love how I just Google like balls swinging hitting each other thing, and it's like, okay, Newton's cradle. Yeah, this is a great little kind of explanation for how like current moves. So you can think about like these balls don't actually like move very much physically, but force is transferred through them, right, through all the contact. And it's the same thing with Coulomb forces in conductors. Again, the individual electrons don't really move that quickly, but they bounce into each other a lot, and that information in the form of current gets transferred really quick. Okay. So where this comes from is the formal definition of current, which is this. And then here, let's get like a little, there should be a little like nice little diagram. Because then we do like volume, charge, density and stuff. Yeah. Okay. All right, let's pull that in. Right. So, good question, Sib. You're asking like, what's the difference between drift velocity and current? This is technically what it is. So, current is the change in charge per unit time, right? And we could think about the amount of charge being Q, like the charge on an individual thing. And this is the density. Or we say like this is the volume density of free charges. So basically saying like, how many free charges do I have per unit space? And then this here, A, this is the cross-sectional area. Of your wire or your conductor, whatever's like carrying the current. I'm just going to say wire because it's usually a wire. And then this here, VD, is the drift velocity. So you see that a lot of things affect current, right? It depends on like how dense, the amount of free charges you have, what the cross-sectional area of your wire is, right? And then it also depends on what the average drift velocity of your electrons are. So it's all kind of like related to each other. So it's a little bit complicated. Yeah, they talk about how like the speed of an electron is sometimes much greater than the drift velocity, and that's true because even though the electron is moving very quickly, it may not be effectively moving in the direction you want it to go very, very well. And that again depends on the structure of whatever material you're moving current through. If something doesn't have a lot of free charges, I don't care how fast the electrons are moving, they're not going to have many other things to hit. So they're not really going to, carry current down very well. Yes, exactly. That's a good way to think about it, Sophia. Yeah, current is the transfer of like effective usable charge, right? Whereas drift velocity is, yes, like the Newton cradle thing, which is, sorry, not the Newton cradle thing. The Newton cradle thing is current because that's like effectively moving charge. Whereas moving the actual charge, yeah, is the drift velocity. Moving the effect of the charge, that's current. Yeah, so they have some questions where you can calculate the drift velocity of electrons. Here's just like a quick little example. I'm not going to do all the math because it's just kind of boring. And I think we probably have a clicker question on it. But here's like an example. Exactly. And Sibley, we think about current as being positive charges, even though it is not. That's a conventional definition of current. So, for instance, here they have an example of calculating the drift velocity in a wire. So they talk about like 12 gauge wire. That's pretty thick wire. Diameter of 2 millimeters. It's carrying 20 amps of current, and they say that there's usually one free electron per copper atom. Okay, cool. So then they calculate, oh, well, the density of copper is this, and the atomic mass is this. Oh, this is a little bit too much. Okay. Well, this is the equation that relates current to this. 20 amps of current, that's your I. So they go into first determining N, which is the density of free electrons. And so here they do like some cool stoichiometry. They say, oh, okay, well, what's the density where for every atom of electron, I have one electron? And it's like, okay, cool. Well, in 6.02 times 10 to the 23 atoms, you have 1 mole of that atom. And for every 1 mole of that atom, you have 63.54 grams. And then you convert this into kilograms. And so this gets you how many electrons per unit volume. Right? So this is the volume density. We talked about this. Volume density means you need like number of things per unit volume, and that needs to be a 3-dimensional shape. That's why it's meters cubed. So here they say that, okay, cool. Well, the volume density of copper is 8.34 times 10 to the 28. And then they go to calculating A, which is the cross-sectional area. So if you know that 20 gauge wire has a certain diameter, you can figure out the circular cross-sectional area of that by just doing pi r squared. And so that gets you A. And then then you have everything you need to do to solve for drift velocity. And what they get is this. So you get a really, really small number. This is really small. This is, what's that? That's sub-millimeter. Yeah. So, yeah, even though, yeah, you got a 20 gauge wire, that's a thick wire. It's 12 gauge wire, that's really thick. You got 20 amps of current. Your electrons they're moving slower than a millimeter per second in terms of the drift velocity. So it's pretty crazy. Yeah. So there's a lot more being done in the bouncing off of each other than there is in the actual movement of the electrons. Okay. So current density, there's a formal way to calculate it, which is J. I don't think we need to calculate much current density, but I guess it's kind of useful. I just want to get to the meat and potatoes of like Ohm's law. That's where this is really like comes in play. This is kind of all the I don't know. It's more the theory side stuff that kind of starts to bore me, honestly. And so I feel for you guys if you're kind of like, wait, why are we learning all these new things? At the end of the day, we're just trying to get to Ohm's law. But it is important to know some of these things because this will come up, especially when you do anything involving like Lenz's law and currents and magnetic fields, you have to start talking about current density, which is J. So this looks pretty similar, right, to like pressure. Remember like force over area? This is current density, which is the amount of current divided by area. And so notice that when you divide by area, since we already said current was defined as NQAVD, now the A's cancel. And you just get that current density is equal to NQVD. So this is like independent of the cross-sectional area. When my friends prefer girls over me, I come here. Oh, yeah, physics will always be there for you, no matter who prefers you. Physics always prefers you. Physics chooses you. Yes. So one way to do this is if you can define current as integrating the current density over the cross-sectional area. So you could, I don't know that this is usually given in your level of question. Sorry, your level of physics. I don't think we deal with actually doing this integral. But in higher level classes, in like upper division E&M, you will be given like current densities that aren't uniform. And in that case, you end up having to do areas where the current density depends on like where you are on the cross-sectional area. But I don't think we have to do that. If it comes up on our homework, I'll do it. But okay, I want to get into the cool stuff, which is like resistivity and stuff. Yeah, here we go. Okay, cool. All right, so we're probably asking ourselves, okay, wait, what drives this current? Like, what drives current? What is causing my charges to, move down a wire, and what's like impeding that and such? So what we end up learning is that J here, this was current density. So think about that as like the amount of current that's like flowing down a wire. And that's going to be proportional to sigma E. Okay? Where this is called the conductivity. And then this right here is the electric field in the wire. So you can think about, right, in our classic question, our classic example, what was it, right? Yeah, right here, right? If you have a really, really strong electric field, right, then you're going to be pushing current a lot faster. And then you can think of like the current density, right? The amount of dq/dt in a certain area, that's also going to go up. It's kind of like flux too, honestly. Current density kind of starts looking like flux. But this also shows you, right, as something is more conductive, then for the same electric field, you get more current. You get more charges that are, flowing down. Okay. So we'll eventually get to ohms later in the chapter, but what they want to talk about here is then going to be called resistivity, which is equal to rho. I know. People are like, bro, haven't we used this thing for like so many haven't we used this letter for so many things in physics? And I'm like, yeah. It kind of also looks like density too, doesn't it? Yeah. Okay. Yeah. Just take my word for it. This is resistivity. And it's equal to 1 over the conductivity. So something that has more resistivity, right, is less conductive. And you can think about, right, that means it does not let as much current flow, given that there's an electric field being created in the wire. And the electric field creating the wire, right, that all comes from the potential difference across the wire. So whenever you look up how conductive different metals are, they're usually going to give it to you in these forms, resistivity or conductivity. So here's like an example of the different numbers in terms of conductivity and resistivity for different materials. So, right, more conductive means you can run higher currents through it and things. So silver, copper, gold, these are all great, right? These are great conductors. And then like carbon is terrible. 10 to the minus 6? Yeah, this is garbage, dude. Yeah. But you can see here, actually, this is kind of cool. So they're all around 10 to the minus 7. But gold, for example, one of my favorite colors, is 8 times more conductive than steel. Yeah. So that means for the same electric field, right, for the same potential being put in a wire, you can get 8 times the amount of current going through it. And this is why, for instance, in computers and things, right, gold, copper, these are all very highly sought after things because they allow electricity and current to move through the components without facing much like resistance. Like they move pretty freely. And this is also why, I don't know, if you see any of the EV chargers, like those all have like big copper wires in them. And then homeless people try to steal them. because copper is worth money, because copper has very good conductivity. I think the one bad thing about copper is that it's corrosive, whereas gold is not. So copper, I think, yes, copper has better conductivity than gold, but it corrodes easier. It oxidizes. So it's not as useful for like long-lasting things, or if you're exposing things to corroding substances such as water or, air, such as things are oxidizing. And this is why copper wires are also usually insulated, right? You want to keep things from oxidizing. That's a chemistry thing. Okay, so those are the different resistivities. We can then also talk about the temperature dependence of resistivity. So we can think about like what happens to the resistance of something as I, go up in temp. Okay, so this is resistivity with temp. And this is specifically for conductors. It's different from non-conductors, but or semiconductors, but we're not really going to deal with those. That's another specialty class. But for conductors, the resistivity goes up with temperature. And that seems kind of weird, right? Usually we think that as we warm things up, right, that it's easier to do stuff. I'm trying to think, like activation energies, lots of things in life. We're like, oh, just put more energy in and things work better. In the case of conductors, they don't, because the hotter a wire gets, remember that temperature is directly related to the kinetic energy of the atoms, like how much they're vibrating, like within the wire. What ends up happening is those vibrations end up causing more blockage for the electrons that are trying to move. So when everything in your wire is just moving really, really fast because you're at a higher temperature, now the electrons, which are the only things you're trying to move to create current, have more things to run into. And so there's a lower drift velocity, so you get like a lower current. Alpha is the constant for that. And then they talk about how that alpha is actually negative for semiconductors. So that was, did they give alpha here? I don't think they did. No. And there's a reason for that, and that has to do with it talks about like impurities and things. Yeah, don't worry, we're not going to worry about that. Okay. So, good. Then we get to finally what I've been trying to build up to it. Resistance. This is just like pure resistance of like a component. Okay, so finally. Resistance. Okay. Which is related to everything we've talked about so far. It kind of all builds into this. And so what we think about is that you can have a material. Let's say this is a wire. It could be a resistor, I guess. And it's hooked up to a battery, right? So this has positive and negative V0 on it, okay? And what happens is that as current from the battery tries to move across this like component, let's say this is like a resistive component. You're going to have, right, high potential here. You'll have low potential here. That means you're driving current this way. It means you have electric field going this way. And you also have current density J going that way. So we learned earlier, right, that electric field was equal to the change in potential over the distance, right? This was like the E equals V over D. Do you remember? We did this a lot earlier. I think it was probably last week. Okay. And then let's remember that current density is equal to I over A, right? So this is current divided by cross-sectional area. That's current density. And then the other property we need to use here is that electric field is proportional to the resistivity and the current density. So let's see, where did we pull that out? I hate when like books are just like, oh, and just remember this. I'm like, okay, but where'd that come from? Where do we do electric field with resistivity? No, that's Q versus C. One sec. That's current We're teaching resistance right now. Resistivity. Okay, this is it. This is what I wanted. Okay. Remember that current density is equal to conductivity times E. Okay, I'm going to pull that in. Conductivity times E. Okay. Now I think we can start like putting some stuff together. Okay. So okay. From this, I'm going to write that electric field is equal to 1 over conductivity times resistivity. So let's write out like what all the things are so you don't get confused, right? So E, that's electric field. Delta V is the potential. L is the length. Okay, cool. Good night, dude. J is current density. I is current. A is not amps, it's area. Sigma is conductivity. Okay, and then this thing, which is equal to 1 over this, that's equal to resistivity. Okay, here are all our little components. I just wrote them all out for you guys. All right, so in this case, I can now substitute this in. I'm going to say, okay, cool. Well, electric field is then equal to resistivity times J. Okay. But electric field is also equal to change in potential over length. Okay, so we can replace that. We say, oh, well, the change in potential over the length is equal to rho J. But J is the same as I over A. So here, I'll try and color code these for you guys. So this is the same thing as I over cross-sectional area. Okay. So then eventually what we get here is that the change in the potential is going to be equal to rho L I over A. Okay? And this right here is what we call like the voltage drop across a component. Okay? So in the case of if you just have a battery hooked up like this, okay, and let's say the battery is like 12 volts, that means you are going to drop 12 volts across this device. And how you drop those 12 volts can be calculated from the resistivity of the material that the voltage is going across, the length of it, the current you're putting across it, and then A. Eventually, this will end up being called resistance. By what we say is like Ohm's law. So they're kind of like they're tempting at Ohm's law, but we haven't done it yet. They say like, oh, resistance is equal to delta V over I. I'm like, cool, bro. Like, what? This really comes from delta V is equal to IR. But yes, okay. So looking at this and this, the I and the I, you end up defining this little thing here. This is equal to resistance. And this is the important thing. If you want to just take away like one thing away from this, it's that resistance is equal to your resistivity, which is dependent on your material, the length of your material divided by A, so divided by the area. Okay? So note that as the length gets longer, the resistance gets more. And so you drop more voltage across the device there. As the area gets bigger, the resistance goes down. And kind of the thinking for this is that, so here, area goes up, resistance goes down, length goes up, resistance goes up. The way to think about this is if you had, for instance, like, let's say like a small area and then a bigger area, right? Now there's more space for the electrons to move without like bumping into things or like positive things that don't really carry the charge they want. So more space equals less resistance. However, if something gets longer, okay, and let's say it's the same cross-sectional area, we say that like more length equals like more mud you have to walk through. I would say like, yeah. Does that kind of make sense? You know, it's you can have like a rough patch, and that's like what resistance is for electrons. And then if you have more of that rough patch to walk through, you have like effectively like more resistance to what you're trying to do. And then with the area, it's like trying to fit all of, you know, these things. You're trying to fit all the amps down the pipe, right? But if the pipe is wider, then the amps don't have to like squeeze through as much. They don't bump into the walls as quickly. Okay. Let's get, I think there's one more, I think we got two more clicker questions we got to get through. This. Okay. A wire consists of a uniform cylindrical tube of a particular material and has a resistance R0. The wire is stretched to double its length, but the material maintains the same density. Assuming that the stretched wire also has the shape of a uniform cylinder, what is the new resistance of the wire? Ooh. This is kind of tricky. Okay. So, let's say we have our first thing. And then this has some resistance R0. Okay. And let's say it has a length L0, okay? And then let's say it has a cross-sectional area A0. And now we have a new shape, which is going to be double the length. Oh, okay. And the material remains the same density. Okay. And, oh, it's being stretched. Ah. Well, not quite. So let's remember, there's actually a lot of really cool stuff going on here. So let's remember that this is the resistivity. Which depends on the material. Doesn't depend on the geometry of the material, it just depends on the material. And that's going to be the same because it's the same thing, right? It's a particular material and it's the same material. It has the same shape. However, yeah, if we start stretching this thing out, then you have to start decreasing the surface area or the cross-sectional area of your device. Because they said that so this is a different density. This is not charge density. This is volume density, right? So you say density, right, is equal to mass over volume. So if you're stretching it further out, Then, okay, and let's see what, like, so the volume of something here, right? This is equal to A times L. So in order for something to have the same density, and assume like we're not creating more mass, right? We're not somehow adding more mass to the tube when we stretch it out. That means that the area is going to have to go down, right? So if this is 2L naught, then in order for you to have the same volume, effective volume, that means now that A, so here we'll say like L1 is equal to 2L naught. We would say that A1 is now equal to 1/2 A naught, right? Think about it. You have a wire, right? And you start stretching it. Maybe you've seen this before. Have you guys like stretch, I don't know, like dough or something out? You ever notice that like it just gets thinner as you do this? It's because the volume of what you have is the same. But volume is always equal to cross-sectional area times length. So if you start increasing the length of something and you want to keep the amount of volume, the amount of stuff that's there the same, you have to start thinning out the surface area. This is actually all they call this extrusions too. This is how they make wire. They take really like thick pieces of wire and then they just like start pulling it. And the more you pull it, the thinner it gets. Oh, this is cool. Okay. So then let's look at resistance, right? Resistance is dependent on L and A. Okay. So if R0 was equal to rho L0 over A0, then your new resistance, R1, is equal to rho, and then it's L1 over A1. But we said the length is now twice, so rho 2L1, and then the area is now 1/2. So not 2L1, sorry, it's 2L0, and then this is 1/2 A0. So now effectively you get a factor of 4 rho L0 over A0, and this is equal to 4R0. Wow, that's pretty cool. It's 4 times your resistance just for stretching out a wire. Because you're adding more resistance by making the electrons travel a longer length, and you're also making their life more difficult because you're decreasing the size of the pipe they get to run down. So yeah, correct answer for that is E. Nice. Okay. We can do, this one's pretty quick. Let's do this one. Could I show the computation more one time? Yeah, sure. Okay. So let's imagine we have our original pipe or our original cylindrical tube, okay, which has a resistance R0. It has a distance, a length L0, and a cross-sectional area A0. I then take this and I stretch it out by a factor of 2 in the length. So I'm going to say L1 is 2L0. Well, in order, so here this is like V0 equals A, or A, and then like V1 has to equal A1, L1. In order for V0 to equal V1, right, I need the volume of this device to be the same because I'm not adding in more copper or anything, right? I'm just pulling it apart and stretching it. In order for the volume to stay constant, if this length goes up by a factor of 2, this has to go down by a factor, or it has to be multiplied by a factor of 1/2. And so that's why the area, the cross-sectional area, is now 1/2 of what it used to be, because the length of it is now twice. And this came from this. The material maintains the same density. So if it's the same density, then it has to be the same mass because you're not suddenly adding more copper in, right? You're just stretching it. That means the volume needs to stay the same as well. So like same. This is kind of weird that they say the material maintains the same density. I would have said, I don't know, that you don't add more material. But I guess they're also talking about like the copper doesn't change in density. Like the raw like atoms shouldn't. Yeah. Okay, so then resistance is rho L over A. So for your original one, this was your original one. It was rho L naught over A naught. And then for your new one, R1, that's been like stretched, now it's rho L1 over A1. Rhos are the same. Now we said that because I'm increasing the length by 2, L1 is now 2L0. And in order to maintain the same amount of copper there, I need the cross-sectional area to then be a half of what it used to be. So now 2 divided by a half is the same thing as 4. And you get 4 rho L0, A0. And then this right here, this was our original R0. So that's why it goes up by a factor of 4. That's a good question. That's a good exam question. Hint, hint. Okay, let me pull this one up. We got 2 more clicker questions. I got 4 minutes. I think I can do it. But let me know, Josh, if that made sense. If not, I can do it again in office hours. Okay, it said if aluminum and copper wires of the same length have the same resistance, which one has the larger diameter? Oh, pretty cool. So we got to do, right? Resistance is rho L over A. So resistance, I'm just going to say big R, equals rho L over A. And this rho right here, right? This is the conductivity. No, it's resistivity, sorry. Conductivity is the theta looking thing. Or sigma, sorry. Okay. So we have to look between copper and aluminum. I'm pretty sure copper has less resistivity than aluminum. Yes. So look, copper, 10 to the minus 8, 1.68 times 10 to the minus 8. Aluminum is 2.65. So we're going to say for copper is equal to 1.68, negative 8. And then aluminum was equal to, I don't know, like 2.6, 2.5-ish. It was around 2. Let's just say it's around 2. Okay. So if they have the same resistance, but aluminum has a greater resistivity, then that means it has to have a greater area or larger. Yeah. So this is, remember, this is the area. Which larger area then means larger diameter, right? So we say, so rho for aluminum is greater than rho for copper. So A for aluminum must be greater than A for copper, so that R for aluminum equals R for copper. Because remember, this is rho. So this is rho AL. We said they had the same length, right? So yeah, that thing's the same. So basically, if this goes up, this must also go up in order for it to equal the same thing. Cool. So I think, yeah, the aluminum has the larger diameter. And that was choice B. Correct. Okay. 1 minute. 1 minute for the last one here. Okay, so this kind of got into like our... This is kind of what we're eventually getting into tomorrow, but we technically covered it... where did we cover it technically? We technically covered it here. So this is Ohm's law. This will be the main thing we go over tomorrow. But, okay, it says currents of approximately 0.06 amps, so 60 milliamps, can be dangerous or even fatal. Currents in that range can make the heart defibrillate, beat in an uncontrolled manner. The resistance of the human body can be 1 kilo ohm to 100 kilo ohms. That's a crazy variation in resistance. What voltage can cause 0.06 amps? Okay. So, I mean, if you rearrange this, right, you get that I is equal to V over R. So, in the first case, where your resistance is a kilo ohm. So this right here, this is resistance. 0.06 is equal to V over 1,000. And then you can also do 0.06 is equal to V over 100,000. Let's see what numbers we get for that. We actually haven't done very many number things, have we, today? It's been a lot of conceptual. Actually, I'm dumb. I don't even need a calculator. What? I can do 1,000 times 0.06. Sorry, that's the me waking up at 4:30 for my flight. Okay, so this is going to be 60 volts. And then this is going to be, move the decimal twice. Was it 60,000 or 6,000? Oh, 6,000. 6,000. Right. 10 to the minus 2, 10 to the minus 5. Yeah, 10 to the minus 3. Okay. So then, yeah, here you go. This is the fatal voltages that can kill you. So that's between 60 volts and 60,000 volts, and it depends on your resistance, right? Yeah, so answer choice to that one would be A. And so, yeah, just some like quick little, real world stuff here, right? Most of your home sockets, if you're in the United States, are at 120 volts, right? So 120 volts is a standard US circuit, US socket, basically. Europe runs 220. So that's like EU. If you're in Europe or somewhere overseas, you probably run 220 instead of 120. So both these voltages can kill you if your resistance is low enough, okay? Notice we talked about like the resistance of the human body. And that has to do with a number of conditions, right? If you are soaking wet because, I don't know, you went in the pool or something, then the resistance of your body is very low because water is, I guess a pretty good conductor of things at that point. It's better than skin. So yeah, this resistance of your human body depends on a lot of conditions. And yeah, that this is why, like, don't jump into the pool if you have like a toaster nearby or something, or don't handle electricity if you're wet, or if it's humid outside or whatnot, because the resistance of your body goes down and it becomes a lot easier for high currents to travel through, and then that causes you to, I don't know, unalive yourself. It's pronounced water. Anyways, okay. Yeah. Main thing here is being that, like, you don't need that much current to really no longer be here on this earth, but it turns out that the resistance of the human body is quite high, and as long as it's in the higher ranges, the voltages required to do that become a little harder to hit, but not impossible. So be safe. Okay, cool. All right. That's it for today. I hope this was informative. I know it seemed a little bit boring going through all the different little terms for resistance and whatnot, but trust me, this will all build up tomorrow when we start actually doing Ohm's law, and then you'll be like, oh wow, resistance is actually really cool. So yeah. Volts burn, amps kill. Yeah, volts like hurt, but amps like are forever. That's kind of where it comes from. Yeah, okay, we have office hours again today. That'll be at 3 p.m., so that's in an hour and 15 minutes if you want to come by and get some help. Also, yeah, please make sure to do the pre-lectures. Those are due tomorrow at 2 p.m., and any homework that's due. I know there's a lot going on. I need to focus on writing your exam for Friday, so that's what's going to be occupying my time. But yes, you're very welcome. I will see you guys later this afternoon. Otherwise, same time, same place tomorrow. Enjoy your Monday. Peace.